Okay, thank you. Thank you, everyone. Already half an hour class was left. So, today I'll discuss you about the K constant. K is a constant for the voltage drops, and K is depends on the voltage regulation, and K is a transmission line constant. So, to derive the K value purpose, I am considering a primary feeder. Okay, primary feeder is nothing but a feeder connection, a conductor which is having a substation to the main transmission distribution transformer. Okay, so where the conductor is there, you have some reactance, you have some resistance. With respect to the reactance and with respect to the resistance, you have some impedance value. Okay, so at the sending end, I am taking a sending end voltage Vs bar. At the receiving end bar, Vr bar. Okay, so Vs bar and Vr bars are there. Okay, I have Z bar. Z bar is nothing but the impedance of that particular transmission line. Okay, Z bar is equal to R plus Jx. So with respect to the Vs and Vrs, you have some I amount of current. Okay, so through that primary feeder, I have I amount of current is there. Okay, and so with respect to the I amount of current, with respect to R and X amount of resistance and reactance values, which gives P amount of active power, Q amount of reactive power. Okay, at the receiving end side, I am taking receiving end active power and receiving end reactive power. Both are different. Okay, PR plus JQR. Okay, in general, active reactive powers are P and Q. Okay, when I go for the receiving end side, PR plus JQR. Both are different. You need to remind this. Okay, so I have Z amount of effective impedance, Z amount of effective impedance for the three phase. Here I have shown the single line diagrams, and three phase means depends upon the nature of the load. Okay, I have different amount of loads. So, for example, when a lump load is connected to the at the end, okay, lump load is connected to the end, the effective impedance is equal to multiplicand of into impedance already existing into length of that feeder main. Okay, depending on the length of this particular feeder, you need to have that. So the effective impedance is equal to already existing impedance with respect to the length of that particular feeder main. Okay, so the effective impedance is equal to Z into already existing into L amount of length. Okay, so this is about the thing. So you need to know about another two things. So when uniformly distributed loads are there, okay, at the receiving end side, some may have the uniformly distributed loads, some may have the non-uniformly distributed loads are connected. Okay, so for that the impedance value may change. Okay, so these two are the important things. Important one, Z bar for the uniformly distributed loads, total impedance value is half of Z into L. This is measured in terms of ohm per phase. Okay, when the load has an increasing load density, okay, when the load has increasing load density or non-uniformly, some may decrease or some may increase, in some way it is increasing, in some way it is decreasing. Okay, when you compare that increasing load density, Z bar is equal to 2/3 of Z into L. Okay, it is depends to the with respect to the length, but when uniformly distributed loads are there, half into Z. When increasing the load density is continuously increasing, the effective impedance is 2/3 of Z into L I have. Okay, I don't have any losses at the receiving end terminal, so I am taking VR is equal to VR at an angle of 0 degrees. Okay, this is about the vector diagram of that. So here how I will get this particular thing. Okay, so this is about the general thing. I am taking VR as a reference with respect to the IR and IX values. I will get the VS amount of thing. Okay, and here is the I amount of current. VR, the angle between the VR and I is theta. This is about the power factor angle. This is about the power factor angle. This delta is nothing but a load angle. Okay, the angle between the sending end voltage and receiving end voltage is nothing but the angle between the sending end voltage and receiving end voltage is nothing but a load angle. The angle between the voltage and current is nothing but a power factor angle. Okay, all of you remind this. Okay, I have this. So Vs is equal to, from the vector diagram, Vs is equal to Vs at an angle of delta. So here this is the positive one here. Okay, Vs is equal to Vs at an angle of delta. I'll get. Okay, Vr is equal to Vs is equal to this particular thing I'll get. So I is equal to I at an angle of theta degrees. Okay, I don't have the any power factor angle. So theta is equal to 0. If if the load is increased, automatically you have a changes in the thing. One, theta is equal to 0. I will have the negative amount of value. So theta minus theta you will get. So the power factor is lagging by the first real power, and reactive power flows in the opposite direction. Okay, when the real power and the reactive power flows in the opposite direction, the power factor is a leading thing. Okay, so voltage regulation is nothing but, in generally you have sending end voltage, you have receiving end voltage. Okay, with respect to those two things, you can determine the voltage regulation, that too per unit values. Okay, per unit values are nothing but the base value divided by MVA loading. So you have this. So VR regulation per unit is equal to Vs. All these things are to be done with respect to the per unit values. Vs minus Vr divided by Vr. Okay, Vs minus Vr divided by Vr you will get that. Okay, so Vs minus Vr divided by Vr into 100 when I am going for the percentage voltage regulation. So percentage of voltage regulation is equal to 100 into Vr per unit. Okay, this is about the voltage regulation. Okay, where the per unit voltage drop value is equal to, voltage drop is nothing but IR cos theta plus Ix sin theta I have. Okay, this is about the voltage drop calculation. Okay, so voltage drop calculation in formulas. So the difference between the sending end voltage to the receiving end voltage with respect to the ratio between the difference of sending end voltage to the receiving end with respect to the base voltage. So there sending end voltage to the receiving end voltage with respect to the receiving end. Here base voltage, both are different. Base voltage is different, receiving end voltage is different. Okay, so you have the voltage drop calculation. Voltage drop is equal to 100 into voltage drop per unit. Okay, so this is a voltage drop calculation. So when I go further in detailed, okay, why I am going for that? Okay, so VB is a arbitrary base voltage. The base secondary voltage is usually selected as, okay, the base selected voltage is usually selected as 120 degrees. The base primary voltage is usually selected with respect to the primary potential transformer. Okay, this base arbitrary voltage is depends on the potential transformer ratio. Okay, so when the potential transformer ratio is 20, base voltage is 2400 voltage. Okay, potential transformer ratio is 60 I have. Okay, if the 60 I have 7200 volts. Okay, and the next Common potential transformer ratio is 100, I have 12,000 voltage you have. Okay, this is about the standard things. Okay, when potential transformer is there, depending on that you are going for the base voltage. Okay, that base voltage you have another name of arbitrary base voltage. Okay, so this base primary voltage is usually selected with respect to the potential transformer ratio used. Okay, potential transformer ratio is 20. I have number of turns ratio. I am saying potential transformer ratio is 20. I have means base voltage is 2400. Okay, when potential transformer ratio is 60, I have 60 is to 1 like that. Okay, 7200 volts. When the potential transformer ratio is 100, you have 12,000 voltage. Okay, so 20 is to 1, 60 is to 1 like that. If 120 voltage I have, okay, so 120 into 20 you need to multiply 2400. 120 voltage I have there, 120 into 60. I am taking the whole primary feeder. Okay, so for this I am going for that. So sending end voltage is equal to receiving end voltage plus IZ I have. Okay, with respect to that, this is about the Vs bar is equal to Vr bar plus IZ bar I have. Okay, so I am substituting the same Vs bar. Vs bar is equal to Vs at an angle of delta plus delta I have. So when I expand that into the polar to rectangular, okay, Vs into cos delta plus J sin delta I'll get, and Vr is a reference one. Vr at an angle of 0 degrees, I'll get the Vr only plus I at an angle of minus theta. I'll get I into, hello, hello. Somebody unmuted. Please unmute yourself. If you have doubt, I'll Nikhil, please give me your doubt. You can unmute yourself. Don't disturb the class, please. So I into cos theta minus j into sin theta I'll get into r plus jx. Okay, these are all the, this is about the quantity. Okay, the quantities in the equation, above equation can be either all in per unit values or in normal units values. Used to line to neutral voltages for the single phase, for the three phase, phase to neutral, phase to phase voltages you need to take. Okay, so this is about the thing. So in general, for the difficult circuit, for the typical distribution systems, R is approximately equal to the X, and voltage angle is much closer to the 5 degrees. Okay, voltage drop is much closer to the 5 degrees to the 0. So 0 delta value is varied from 0 to 4. Okay, so almost the load angle is 0 degrees. Okay, for a typical transmission system, delta value is 0. For a distribution system, for a typical distribution circuits, R is approximately equal to X. Vs I have, Vs is equal to, when the delta value is going to 0, only cos delta you will have. Sin delta will become 0. That's why I am neglecting that components. Vs approximately is equal to Vs cos delta plus j into Vs sin delta. That sin delta will goes to 0. Okay, so because of that, and since x is much larger than the r, therefore for a typical distribution circuit, sign value may neglected. Vs approximately is equal to Vs into Vs bar is equal to Vs into cos delta. Okay, Vs is equal to Vr plus Ir cos theta plus Ix sin theta I'll get. So voltage drop is equal to, voltage drop per unit is equal to, I got this. voltage drop per unit is equal to Vs minus Vr. Vs minus Vr is equal to IR cos theta plus Ix sin theta divided by Vb. That is about the base voltage. So always this voltage drop per unit voltage drop value is positive quantity. So voltage drop is negative. There are possibilities of negative values also when there is a leading power factor. When there is a leading power factor due to the shunt active capacitors, or where there is a negative reactance, where there is a negative reactance due to the series capacitors installed in the circuits. Okay, this is about the voltage drop per unit calculation. Are you having any doubt? Okay, I'll go with that. So the complex power at the receiving end, here I have at the receiving end is PR plus JQR. I have taken the PR plus JQR is equal to VR bar into IR. I'll get I conjugate I get. Okay, these things you know that I is equal to PR minus JQR divided by VR. Okay, this is about the I value. Okay, I conjugate means this particular value may get negative values. Since VR bar is equal to VR at an angle of 0 degrees. So I am substituting that components in the above equation. See here, there, here. I values I am substituting. I values I am substituting and VR values I am substituting here. Okay, so Vs is equal to Vr at an angle of 0 plus Rpr plus Jx into Qr divided by Vr at an angle of 0 minus J into Rqr minus Xpr divided by Vr at an angle of 0. I'll get. Okay, so when I extend this equation, delta angle is not neglected. Okay, delta angle is not neglected. So automatically this J value is going to 0. Okay, that J value will become 0. Why means here the PR, the difference between the PR and QR is negligible. Okay, so negligible means which is compared to the which is approximately equal to the 0. So this particular value may goes to 0. So I am writing Vs is equal to, in terms of Vs approximately equal to the Vr at angle of 0 is equal to Vr plus Rpr plus x into Qr divided by Vr. You will get x into Rpr plus x into Rpr plus XQR divided by VR, you will get. Okay, this is about the sending end voltage. When I go for the voltage drop per unit value, RPR plus XQR. Why? This is about the particular value. Okay, Vs minus Vr divided by Vb now. So Vs minus Vb I have, okay, and divided by Vb. So voltage drop per unit is nothing but this is the thing. What is R value? What is R value? SB divided by VR into apparent power divided by receiving end voltage into cos theta. I am substituting that. So voltage drop per unit is equal to apparent power into R into cos theta plus S into X into sin theta divided by receiving end voltage into base voltage. This is about the voltage drop per unit value. Okay, by per unit, when I go for the per unit base voltage, I will get. Okay, this is about the voltage drop. Okay, so I have PR value. PR is equal to SR into cos theta. QR is equal to SR into sin theta. SR is nothing but VR into I. SR is with respect to the receiving end. QR is reactive power with respect to the receiving end. So theta is the power factor angle. So those things I am substituting. This active power you will measure in terms of watts, reactive power you will measure in terms of VAR, and finally SR is equal to square root of PR square plus QR. That is nothing but the VR into I. Okay. See the about this this particular value and this particular value can be either in a per unit value or in a SI units. Okay. So always remember for the single phase line to neutral, for the three phase line to neutral or phase to phase voltages. Okay, phase to phase voltages you need to take. Okay. So voltage drop per unit is equal to RPR plus XQR divided by VR into VB I'll get. Okay, this is about the voltage drop per unit value. So what is exactly? So when I go for the in-depth of this particular thing, okay, when I go for the in-depth of this particular thing, you have, I am going to take the particular commons. So when I go for this particular areas, okay, this is about the PR, XRs are there. I am going to have this R, this X as an extraction. Okay, so voltage drop per unit value is equal to voltage drop per unit value is equal to so R cos theta plus X sin theta. So for the three phase I am going for, and it is in the per unit value. So 1/3 you will get. So S three phase into S into R cos theta plus X sin theta into 1/3 I'll get 1/3 I'll get divided by voltage receiving end voltage and base voltage. Okay, this is about the calculation. Okay, so voltage drop per unit is equal to apparent power into apparent power of the three phase into K. Okay, this is about the basic formula. Okay, so from this you can easily calculate the apparent power of that particular thing. So already you have the voltage drop per unit, already you know that S3 phase S values, you can easily determine the K value. K is equal to, this is the one, R cos theta plus X sin theta into 1/3 of 1000 divided by VR into VB I'll get. VR into VB I'll get. This is about the per unit values. Okay. So how I'll get the 1000 values, sir? You have this particular thing, okay, in your brain. So when I need per unit values are nothing but you need to transfer the whole KVA, this particular KVS into the volts. So you need to convert that VS into the KVS to the VS. So K is nothing but the 1000 kilo. So that 1000 I have represented here. Okay, 1/3. So for the three phase, you will get the 1/3, and here S3 phase you will get S3 phase you will get. So S. See, previously I have the S. How I'll get the S value? You know that. Okay, how I'll get the S value and how, what is the difference between SR and S? This is about the voltage drop for the three phase. Okay, voltage drop for the three phase is equal to the reactive power into this particular voltage. That too I am converting that into the per unit. So into 1000, 1/3 of 1000 divided by VR into VB. Okay, so this is about the calculation. Okay, finally I'll get the K value as like this. Okay, I told you voltage drop per unit is equal to already existing KVA loading into K constant into three phase. Okay, this is a per unit volts. Okay, like that I have this particular thing. So therefore K is a function of conductor size, spacing, power factor and base voltage. Okay, conductor size, spacing, power factor, and base voltage. This is about the K value. Okay, and it is has a units of volts per kVA meters or miles. Okay, or miles. This is about the calculation. Okay, for the to get the percentage voltage drop of K value purpose, again you need to multiply the 100 value. Okay, again you need to multiply it by the 100 value. It is also having the units of percentage of voltage volts, percentage of voltage drop per arbitrary number of kVAs into meters or miles. This is about the K value. Okay, tell me any doubts are there, I'll let me know. Slide 259 open చేయండి. Yeah, tell me. I think it is H1. First one. Yeah. Tell me. What's your doubt? Okay now. Anybody is having doubts? Let me know. Side. Open చేయండి. Side. Slide up. I'll share my complete notes of this particular thing. I have shared, few of the people are also asking. I have shared first unit notes. Right now we are in second unit. If I finish, if by Monday or Wednesday I finish the whole classes, whole second unit, I'll share the second unit notes also to you. I did handwritten notes. This is about the second unit, third unit, fourth unit, fifth unit. I have shared the first unit. I'll share right now. Please download it and prepare. I'll show you. See, this is about the notes. You can download. Acha, you have some problem to download. I'll share these things to your CRs. Yesterday, your friend, your CRs have called me and they have messaged me. I'll share the A section and B section people through WhatsApp. Is it okay? Okay. I think you have some problem. Can I go for the next topic? You have at 12 o'clock, at 11:45, you have any class? Okay, okay, okay. I go. Oh, 12, 12, 12 का class start. At 12 o'clock, 11:30. Okay, 11:30 అవుతుంది. Go with the next one. So I think I need to have some problems. I'll go with some problems in the first unit. So nothing is there. Actually, by the seeing of question, most of the people are uh, having some problem. So assume that there are six residential customers connected to a distribution transformer. Okay, so here six loads are connected here. Note the code. All the things are nonsense. Is there? None. Notice that code in the customer account number is 4276. The figure 4276. This customer number is 4276. Okay, and figure 4 stands for the feeder F4. Okay, feeder F4. I have the tapping. Indicates the lateral numbers connected to the F4. 1, 2 laterals. Okay, these two are the laterals. Okay, laterals. Finally, the last figure 6 in the house numbered connected to the distribution transformer. Okay, from this distribution transformer here. Okay, so this is about the assume that the connected load is 9 kilowatts per hour per house, and that the demand factor and diversity factor of the six houses, either from the company's records or from the relevant handbook, have been decided as 0.65 and 1.10. Okay, demand factor as well as diversity factor he gave for the six groups. Okay, for the six groups. So determine the diversified demand of the group of six on the distribution transformer. Okay, so you know that diversified demand is equal to total connected demand into diverse demand factor divided by this particular thing. Okay, each load, total connected load is nothing but 9 kilowatts. Okay, diversified demand is equal to total connected load into demand factor divided by diversity factor. Okay, this is about the one thing. Diversified demand is nothing but common demand. Common demand, okay, one or two times it is repeated. Diversified demand is equal to total connected load. Each load is connected to the 9 kilowatts he gave. Okay, 6 into 9. 6 into 9 divide into demand factor. Demand factor is 0.65 he gave. Okay, divided by diversified factor. Diversified factor is equal to 1. This answer is 31.9 kilowatts. Okay. See, within two lines, I'll finish the whole problem. If you know the formula. Okay. So he asked about the writing of that particular thing also. Okay. So 4276 is a this sixth feeder. You need to indicate this. Okay, he will give this particular thing. 1 2 3 4 feeder pattern is there. Here is the substation. Okay, you need that these two are the laterals and bilaterals are nothing but this, sublaterals are nothing but this. Okay, which gives the connection to the customer identification number is 4276 and the distribution transformer is having some name DT427. Okay, so here he gave the data also. Okay, so to get the diversified demand purpose, we have the formula total connected load into demand factor divided by diversified factor. You have diversified factor you have for the group wise. You have the total connected load. Individual load is having 9 kilowatts. I have 6 into that. You have the total connected load. What I will get 54. 54 into 0.65 is the demand factor. Diversified factor is 1.1. Okay, so diversified demand is nothing but 31.9 kilowatts. Yeah, I'll get. This is about the highest one. Okay, this is about the first problem. Second problem, when I am going for that, can I go for the second problem? Hello. Okay, assume that four feeder four feeder pattern system peak of as equal to the system peak of 3000 kVA per phase and copper loss of 0.5% at the system peak. Okay, 0.5% at the system peak. Is it okay? So determine the following: the copper loss of the feeder in kilowatts per phase, and the total copper loss of the feeder in kilowatt per 3 phase. Okay, per phase, per 3 phase I need. Okay, with respect to that 0.5% I will have 0.5 divided by 100 into system peak is nothing but the I square R. Okay, the total copper losses is equal to I square R is equal to system rating. System rating at how much percent? So I square R is equal to 0.5% into system peak. 0.5% is nothing but 0.05 divided by 100. 0.005 into system peak is already given as 3000. So which will give the 3200 kilowatts. Okay, when I go for the solution, 3200 thing I will get. Okay, this is about the 3200. Here 3000 I think. Sorry. 3000. Okay, 3000. This 315 kilowatts I will get. Okay, so this is about I square R. You have kilowatts per phase. Okay, next when I go for the Second one, for the three phase. For the three phase purpose, 3 into 30. 3 into 15. 3 into 15. 3 into 15 is nothing but 45 kilowatts. 45 kilowatts per three phase. Okay, it's not root 3. 3 into I square R. Okay, when I go for the copper losses, for the three phase I square R you will get. For the single phase you will get the I square R. For the three phase, 3 into I square R I will get, you will get. Okay, this is about the second problem. So this is also another problem. I'll share these are the things to you. So please post your roll numbers. One or few numbers. అది చేయాలి. ఇదే కదా క్లియర్ అంటే ఇదేనా ఇందులో వస్తుంది కదా ఇక్కడ సార్ సరే ఇదేమి స్టార్ట్ క్లియర్ చేస్తుందా అలాగే వస్తాయి ఇప్పుడు మళ్ళా. హలో, డోంట్ లెఫ్ట్ ప్లీజ్ పోస్ట్ యువర్ రోల్ నంబర్స్. పోస్ట్ చేస్తుంది మనకు అదీన్ వైజ్ మనకు సింపుల్గా డేటా కొట్టుకోవచ్చు. కరెక్టా కదా? సీనా చేస్తున్నారు 130 ఎంత ఎంతమంది 139 మెంబర్స్ ఇన్వైట్ అయ్యారు. నువ్వు కూడా కదా 73 మెంబర్స్ పోస్ట్ చేసారు వాళ్ళు. నేను పెడితేనే ఉన్నాడు. డైలీ కండక్ట్ చేయాలంటే సినిమా గేట్ క్లాసెస్ ఇప్పుడు అదే మాట్లాడాలి. ఇప్పుడు వాళ్ళకి ఇవన్నీ నోట్ చేసుకోవాలి. ఇది మనకు వస్తుంది సినిమా చాట్లో డౌన్లోడ్ చేస్తారు వస్తుంది మొత్తం వస్తుంది. అదే వాళ్ళు రోల్ నెంబర్ పోస్ట్ చేయట్లేదు. వాళ్ళు పోస్ట్ చేస్తే మనం డైరెక్ట్ క్యాచ్ చేసుకోవచ్చు. కరెక్టా కదా? వైఫై 1 2 3 4 5 6 7 8 ఇంకోటి ఇది ఎందుకు వస్తుంది? రెగ్యులర్ రూల్ నెంబర్స్ మిస్ అవుతుంది సార్. Triple 16. Okay, thank you very much. Still anyone? Anyone is missing? Notes పెట్టాను. This is about close చేసేది. Thank you very much.